Hello students, welcome back. Let us resume our discussion in section 5. Previously we went through prime harmonic series, a famous theorem by Euler. So 1 over nth prime number, that series, goes to infinity. And what's the implication of that? Well, there are plenty. So this thing is, as a matter of fact, 1 over 2 plus 1 over 3 plus 1 over 5, 7, 11. Okay, that's enough. Dot, dot, dot. And that goes to infinity. So there are a lot of prime numbers. Now, compare that with some series like this. And what does that suggest? There are a lot more prime numbers than square numbers, so that this thing adds up to infinity. That's one way to answer it. Also, another way to answer it is prime numbers grow a lot slower than n squared order. And speaking of n squared order, you can rewrite like this. NES, as long as s is greater than 1. Ooh, with all those fractions and primes and so on, you cannot really read it. So, okay, let me expand the font. So compare this with that. Prime numbers grow a lot slower than n to the s power for any s greater than 1. That's the kind of conclusion you can draw. You see, prime numbers grow more quickly than just n. You see, if you take s equals 1, then it's going to be n. N grows as 1, 2, 3, 4, 5, 6, 7, 8, like that. And Pn grows as 2, 3, 5, 7, 11, 13, and so on. So Pn grows more quickly. But compared with any n to the certain power, whenever the power is greater than 1, 1.0000000 whatever 0 and then 1, still it's faster than the growth of the prime numbers. And what's well known is the growth of the prime numbers turns out to be asymptotically equivalent to of this, n log of n, and therefore if I take the reciprocal, that's gonna be in the order of 1 over n log of n. And then how about the series with 1 over n log of n? You can prove that series goes to infinity by the integral test. Remember this? Integral to say infinity. I cannot start from 1 because denominator will become 0. And then, do you remember this antiderivative? So we have log of infinity minus log of 2, something like that. So in any case, it's infinity. Thanks to this integral test, you can prove that series with 1 over n log of n is divergent to infinity. So, okay, all right, let me copy and paste this thing. No, let me copy and paste this thing. And start from 2, because if I start from 1, then log of 1 is 0. So that's infinity, and that's coming from the integral test. And then we know that Pn is in the order of n log of n, thanks to that prime number theorem proposed by Gauss-Legendre conjecture, and then solved by Adamar and Poussin. We are talking about this Gauss-Legendre conjecture, this one here, as an equivalent form of either this or that, later proved by Adamar and Poussin. Thanks to that, we have this growth order, which is far quicker than any of the 1 over n to the s power, where s is greater than 1. And that's related to this prime harmonic series theorem, basically. And as a matter of fact, historically speaking, this proof by Euler opened the door for these kind of treatment. Okay, we went through the proof already, so let's not worry about the proof. But as for this alternative viewpoint, especially the integral test and this thing here, please remember, because we're going to use it pretty soon. This one here in particular. What am I talking about? Let's open 5.2, Euler's product formula. And that too is by Euler. We already went through one humongous contribution by Euler, and this is another one by Euler. And we have, very, very intimidating identity here. Left-hand side, we have an infinite product. Right-hand side, we have infinite sum. And look at the right-hand side. Does it look like something we studied before, just now? N to the negative s power. It's the same as 1 over n to the s power. When s is greater than 1, then by integral test, this series converges. And as for the left-hand side, 1 over 1 minus, this too can be written as s power like this. So we can rewrite like this without using negative power, or you can write like this if you don't mind negative power. I prefer the former form, but most of the textbooks are written this way. Okay. Let's prove that. By the way, left-hand side, in this infinite product, what is this, pi? The same as before, the sequence of all prime numbers in the increasing order. So 2, 3, 5, 7, 11, and so on. Okay, how do you prove it? First, let's begin with the left-hand side. Inside the product 1 over 1 minus of this, you can apply the geometric series formula. And then s is common. So you can write it as pi to the negative s power. As a matter of fact, let me take one additional step here. Pi to the negative s power to the m power. Okay, there goes the geometric series formula. The common ratio that is being multiplied over and over again is pi to the negative s power. And that's for 0 power, 1, 2 power, 3 power, 4 power. So we have geometric series. So the inside of the product can be written as a geometric series. So what is this product then? You can consider this as this geometric series times the next geometric series times the next geometric series, and so on and so forth, for the primes p1, p2, p3, p4, and so on. So far so good. Just using the geometric series and then putting those into this infinite product. Now, how can we expand this? Well, it's a kind of extended FOIL method. First, the smallest is to select all ones, and then next smallest is p1 to the negative s power, and then all others will be 1, and then p to the negative s power, all others will be 1, and so on and so forth. The general term is like this. select anything from here, select anything from here, select anything from here, and so on, and then multiply up. If you do that, what do you get? Well, basically you're going to get something like this. Some pi to the certain power, p1 to the certain power. For example, p1 to the negative 2s power is selected. And here, p2 to the negative 5s is selected. And then and so on and so forth. And then some pk to the negative 17 power is selected. And then bunch of ones. And then, of course, you can consider many, many more so that these products can reach arbitrary length. And then consider them all and add them all up. That's basically what you get. So basically, all possible powers. And then let's make this observation. Whatever multiplication I do, if I have infinitely many strings, then for s greater than 1, so we have negative prime to the negative s power. If I just infinitely multiply all those will go down to 0. That limit will go down to 0 because s is greater than 1 and then it's negative s power. So denominator is getting bigger, bigger, bigger. It's just keep multiplying infinitely many. They'll all go down to 0. If you multiply only finitely many times and then bunch of ones, only those will give you a non-zero to add. And in that case, these product of primes will become an integer. And also, every integer can be decomposed uniquely by those kind of product of primes by the fundamental theorem of arithmetic. All right? So here in this expression, if you have infinite product or 0, that limit is all 0. So we only consider finite product, which means finitely many primes and then bunch of ones. And by fundamental theorem, all those correspond uniquely to integers. So adding up all those possibilities versus adding up all those integers is the same by the fundamental theorem. So what do you have? This original infinite product and the original infinite series are the same, thanks to this geometric series and that argument and the fundamental theorem. Tricky to understand? Remember, we only have finite products left. All the infinite products will become 0 because that's a limit computation. So we can apply fundamental theorem. That completes the proof. So what do we have? This series expression and this infinite product expression are the same. And look at the infinite product. They're determined in terms of prime numbers. So this infinite series must have a lot to do with prime numbers. Indeed, that same expression, that common expression, is defined as a function and zeta of s, and this thing is called Riemann's zeta function. And we did this for real numbers greater than 1, but we can actually extend the same idea for all complex numbers with the real part greater than 1. It's not difficult, but we need some complex analysis. And then we can extend further to entire complex planes through the idea called analytic continuation, but that's really out of our scope. And as for Riemann's zeta function and Riemann hypothesis, I'm sorry, we need analytic continuation, so I'll stop here, except this is going to be the most important and the hardest number theory problem, that is Riemann's hypothesis.